Hey everyone, I'm Christopher DeBella, and you are watching Discovering a User-Facing Concept. So I've been interested in using and writing concepts for a few years now. I think about 2016 is when I started developing an interest in them. And I thought for a while that I understood how concepts were supposed to be written. And then Eric Niebler decided to tweet this back in 2018, and it really shook up the way in which I thought about writing concepts. He said that although concepts are constraints on types, you don't find them by looking at your types in the system, you find them by studying your algorithms. And since then, I've really changed the way in which I've thought about writing concepts. But when I've spoken with people, they pose questions that show that they are still a bit confused. And so I figured that maybe a talk, now that we have had concepts in standard C++ for a little bit now, we should really be looking at how to use the language feature effectively. And that means that this is not a talk on how to use concepts, the language feature. You should already know how the language feature works in C++. And if you're unfamiliar with that, the concept syntax, please go and watch Andrew Sutton's Concepts in 60, everything you need to know about concepts and nothing you don't. It's probably the best concepts talk that I've seen to date. One of the reasons for this is that it goes into appropriate usage itself without drilling into the esoteric complexities of the language feature. And Andrew was one of the principal authors of the Concepts TS and really championed what actually ended up being in C++ 20, as well as being one of the people who wrote the paper that was the precursor to Eric Niebler's ranges movement in C++ 20. This is a talk about generic programming, which means that we are going to be spending a lot of time thinking about analyzing algorithms and working out what their requirements are. If you aren't familiar with what generic programming is, or you need a 101 on generic programming, please watch Sean Parent's history lesson on generic programming from Pacific++ titled Generic Programming. And whenever I talk about Sean's keynote in this session, I'm definitely talking about Sean's Pacific++ keynote from 2018, not his upcoming one on Friday. There are more than a few people that I would like to thank for helping me with this. The people that are listed are people who have provided feedback in some form or have done something to get me into a position where this talk could be delivered. The talk is going to be broken into essentially 3 acts with an epilogue following on if there's time. I will be taking questions at the ends of Act 1 and 2, and then depending on whether or not we have the epilogue, I may or may not take questions at the end of Act 3. So let's get started, and we're going to circle back to Eric's tweet, where he talked about finding concepts by studying algorithms. Now, people have said to me, Chris, I don't necessarily use the STL algorithms. Or what about if I want to have some sort of concept that defines a class of types? How can I go about writing a concept? And so let's start off by working out what an algorithm is. An algorithm is, I put 2 different definitions of the term algorithm from 2 very popular university textbooks on the subject. But essentially what they're both saying is that an algorithm is a solution to a problem where we have some sort of computational procedure that takes an input and gives us an output. That's pretty much it. What I'm really trying to drive home here is that the term algorithm is not restricted to functions from algorithm and numeric headers. This means that if you have a GCD or if you have an A-star algorithm and they're not necessarily range-based, they still count as algorithms. They're just functions that solve some sort of problem computationally. That's it. That's all you really need to know about the term algorithm. Now, we are going to be looking at a range-based algorithm in this particular talk because that's where my background is, but that does not mean that you need to have a range-based algorithm. In fact, the literature dives into things that are not range-based far more often than range-based stuff initially. And then we come to the second question that people ask, which is, well, what does this mean for types? Can we write a container or a number concept? And please do not do this. concepts are not the C++ equivalent to Java and C Sharp's interface keyword. We don't use them for defining what the properties of a type should be. And even if we did, what this is going to do is it's going to cause a lot of problems with us having a fully functioning algorithm, because algorithms don't necessarily use everything that an interface provides all the time. For example, the container named requirement from CPP reference has a member function called max size, but that is, at least in my experience, very infrequently used. So concepts are not a mapping to another language's interface keyword. That's a completely different language feature that has some small amount of overlap. Concepts find themselves derived from generic programming, which is defined as by the authors of From Mathematics to Generic Programming as an approach that focuses on designing algorithms and data structures so that they work in the most general setting without loss of efficiency. And then they do mention that people who work with the STL will start to question whether on what about things like template metaprogramming? Isn't that a part of generic programming? And they go on to say that that is facilitating generic programming in C++, but it is not really generic programming itself. And this is important because it really boils down to generic programming being an attitude toward programming, not some sort of specific thing in C++. And I draw a parallel to object-oriented programming here, in that templates and metaprogramming are about as related to generic programming as classes and member functions are to object-oriented programming. That is, they facilitate it, but they are not at all what embodies it. You don't do object-oriented programming by writing a class. You do it by using classes to do something with the class and the design of your program. Generic programming is very much the same with respect to templates. Generic programming also has very strong ties to abstract algebra. It really did come out of abstract algebra. Now, Wolfram MathWorld defines abstract algebra as the set of topics that deal with abstract algebraic structures rather than the usual number systems that we deal with in everyday life. From Mathematics to Generic Programming says that one of the remarkable things about abstract algebra is that we can prove results for structures such as groups without knowing anything about either the specific items in the group or the operation. Now, if you're not familiar with groups, Steve Downey does a great job of talking about groups in his session. You should go and take a look at that one. But essentially, it's a mathematical description of some collection of objects and an operation that follows some set of rules. Now, I do want to labour on this passage for a little bit longer and reread it to you with a bit of emphasis. So, the passage is, one of the remarkable things about abstract algebra is that we can prove results for structures such as groups without knowing anything about either the specific items in the group or the operation. Now I'm going to draw this parallel back to generic programming. This is a slight modification that I made into the passage. One of the remarkable things about generic programming is that we can prove results for concepts such as ranges without knowing anything about either the specific items in the range or the operation. And let's go back and forth a bit just so you can see the visual difference. There's not really that much of a change. I changed a few nouns, but the sentence still holds its integrity. And so what I like to think about this connection is that generic programming is the bridge between abstract algebra in theory and programming, in this case, C++. And from this, because I've been talking about abstract algebra for a bit, you might be concerned that you need a background in abstract algebra to follow on with this talk, and you don't. Provided that you can understand the top bit of code and see how it can translate into the second bit of code and how they both hold the same meaning for ints, but the second bit of code also covers many more situations that describe exactly the same context, then you should be good. I'm not a mathematician by training. I did fail quite a few math classes and barely passed the ones that I did at uni. So I'm really hoping that this particular slide gives you a bit of confidence that you don't need to be a formal mathematician to understand everything that we're going to be talking about in this session. Let's loop back, because this is a talk on concepts and I haven't really spoken about what concepts are. So a concept is really just a named requirement for some set of requirements. Sorry, concept is a named set of requirements for some algorithm or data structure. And these requirements come in three inextricable forms. And what I mean by that is that where you find one, you will usually find the other two spontaneously appearing, because that's how concepts work. Essentially, there are three different requirements. We have syntax requirements, which are colloquially known as constraints. A constraint is something such as requiring the syntax of ++I on an iterator. The semantic requirements are colloquially known as axioms. And an example of an axiom would be that ++I moves the iterator to the next element. And then finally, we have complexity requirements, which don't have a fancy name, but an example of a complexity requirement is that the ++I operation does that in constant time. So that's where all three kinds of requirements come in, and we'll be coming back to this throughout the talk. The next thing to cover is that the title of this talk was originally designing a user-facing concept. But when I was talking with Eric Niebler about syncing our talks, because I wasn't sure if there was any overlap, it turns out that there isn't. But when we were talking about this, he pointed out that we don't design our concepts. We design our algorithms, and we end up finding our concepts by studying the algorithms. Just like plants and animals, mathematics simply exists. Some postulate that even in the absence of matter and energy, mathematics could still exist. We essentially invent notation to describe maths, but we don't invent the rules for it. We also don't design our relationships between objects. We simply observe and report them. Concepts describe the relationships between types and objects. That's why we discover them. We don't design them. What both Eric and I are trying to say here is that we always need to consider use cases before we start thinking about writing a concept. Always need to think about the use cases. And so that brings us to the end of Act 1. So I'm going to pause for about 1.5 minutes and take any open questions. Okay, I'm not seeing any questions in the chat, so let's move on to Act 2. And as I promised, we need to consider looking at use cases. So here are some use cases. And this is a little bit of an interactive thing. I've got 6 examples on screen, and I'll give you a moment to read them. And could someone please tell me what they think these 6 algorithms are describing? Okay, so they're all left folds. And if you're not familiar with the idea of a left fold, essentially we start out with some sort of accumulator, and we iterate over the elements and collect them into from being in some sort of sequence of elements, which is sort of like a vector, into some scalar. And these pop up in very many places. The summation from maths, or a product operation, is a form of a left fold. A lot of the STL algorithms are actually left folds. Connor Hoekstra goes into detail a lot on that in some of his talks. But the 2 examples in the middle, I think, are all of and any of. And then the one on the bottom right is an example, is an implementation of max element. So these are examples of us having left folds appearing just spontaneously in other algorithms. And Barry Rebson wrote a proposal titled ranges fold for C++23. We'll slowly be working our way through what's proposed in that through Act 2. What I do need to say is that Barry has put a lot of work into this, and really want to thank him for that work. What I need to point out is that P2322 is known as a proposal that does not guarantee that it will ever be made standard C++. And anything that is standardized may be different to what we'll end up talking about in this session. It's a proposal, not a promise. And what I'm talking about is related, but I'm not guaranteeing that we'll ever get anything. So the first thing that we need to do is normalize the code. You may have noticed that the examples that I gave were in 3 different formats. And when we want to do when we want to generalize an algorithm from being a concrete use case into some abstract algorithm, we need to really have them all in the same format. So that way it becomes easy for us to prove that the algorithms are the same and they are all solving the same problem, just with things slightly tweaked. So the first thing we want to do is take this compound operation and turn it into an infix operation. This brings us to the same format as the and the or examples, but it's still not great because it's an infix operation, and in C++, most of our operations want to be are done in a prefix mode where we have the function's name at the front, and then the 2 parameters are inside parentheses. This is not that format, and so what we need to do is we need to normalize it again and end up with a format that is in the function syntax. And so this is what we end up having for the 4 infix things. I couldn't fit the logical or on screen, but it is also adhering to this. And so once we've got this in our final format, we can now start thinking about the properties that we can point at and say these are things that we want to be talking about in a general setting. So I'll give you a moment to digest what properties we can see on inspection, but I'll give you the first one that I could see on inspection, just that way you've got an idea of what I'm talking about. And that is that we're iterating over a sequence, which means that the algorithm is using a range. All right, so the next thing is that we read what we end up iterating over. In both cases, we have I as something that we are passing into plus and max. And that means that we are actually reading it. And so we have what's known as a readable range. And the next thing that I noticed is that we never look back at previous elements. We're always looking at the current one and then moving on to the next element, but never looking back. And that means that it's what's known as a single pass algorithm. We only ever consider the current element. And that will come into play in just a moment. Our operation takes 2 parameters as its input. So it's a binary operation. And finally, the operation returns something that's directly assigned to our accumulator. The accumulator in both cases is, in the first case is sum, and in the second case, it's max. All right, so let's now parameterize the algorithm, which means that we're going to templatify it, and we'll apply some concepts that are in the low-hanging fruit category. The concepts that we're going to be applying are input iterator and Sentinel-4. If you're not familiar with those, Tristan Brindle gave a great exposition on ranges terminology back in CppCon 2019. So these are the 2 easiest of the requirements to add, and they're derived from the first 3 properties that we could see on inspection. But there's, and the code that we see here is very reminiscent of std accumulate, but we can improve it. And so what we have here is another concrete use case where we're concatenating strings, and this may not be the best way to concatenate strings, but it's one of the fastest ways for me to communicate what I want to be communicating here. And so while we preserve the left fold operation here, how can we improve this code? What I have in mind here is that because we're preserving the left fold operation, it's important to note that we are reading spaceless sentence and then immediately writing back into it. So we never need what we are reading from it more than once. That means that we can move the spaceless sentence into the concatenation operation, and then whatever spaceless sentence gets back is going to be the new value. So that's the improvement we want to make. And so now we can apply that to our abstract algorithm. So that way we take advantage of this in situations where performance may be impeded because of a copy and then direct assignment into the thing that we just read from. And now that we have this as our algorithm, we can finally move to analyzing some more of the requirements. So we start out by looking at the main part of the algorithm, which is the invocation. But we start out by considering the initial value. Because we're moving our initial value into the operation as its first parameter, we need to say that it's move constructible. And then because we're getting something back out, we need it to also be move assignable. And when we have these two requirements, we're saying that this needs to be movable. So that's the first thing that we can say about our algorithm, that T now needs to be movable. And now that we've got T out of the way, we can start thinking about our operation. What we want to say here is that our operation is something that we can invoke, where the first parameter has the type T and the second parameter has the iterator's reference type. And so once we've had these three bits of information, we can say that op models the invocable concept with respect to T and the iterator's reference type. And we can apply that as our second requirement. Now, because we are assigning to the initial value to our accumulator, and the invocation's result may be a different thing to the actual type T, we also want to say that the invocation's result is assignable to the T. And then for reasons that I can't remember, we also want op to be copyable. And so now we've established the requirements for that describe the relationship between T, the invocable, and the iterator's reference type. There's quite a lot here, and it isn't really digestible. Digestibility is something that I will be uncovering with Cybran tomorrow in our documentation talk. But because it's not really digestible, what we want to do is we want to abstract this away into what we call a detail concept, which is something that's not user-facing, which means it doesn't meet the criteria for the title of this talk. And essentially, we structure it in a way that will give us the best possible diagnostics and describe the requirements in some way the compiler can understand. That's really the only difference between what you saw on the previous slide and what you see now. And so there's no real structural change, except that we are making it a bit easier to digest what this algorithm's interface is. And then we've really come to the end of what std accumulate looks like in C++20, but with some requirements attached to it. But then someone comes along with a new use case, and they want to add a bunch of numbers. In this case, we have 1.0, 0.75, and 0.25. And so when they pass in 0.0, they get back 2, which is great because that's the correct answer. But when they pass in 0, they don't get the correct answer. They get back 1. And the problem here is that the code that we had on the previous slide will amount to this. We essentially have an int sum, and then thanks to double to int conversion, 1.75 will be truncated to 1, as will the subsequent 1.25, and so the result will actually only be 1 instead of 2. And so Barry presented a fix for the proposed left fold, which is what's on screen here. And it addresses the use case that we've just presented, where we may want to pass in an integer as our initial value, but get back the correct answer, which is 2, not 1. Sorry, the correct answer in theory. Make the theory and the practice in sync. And so the way in which we do this is we take the invocations result type that we were talking about a moment ago, how it may or may not be the same thing as T, and use that as our left fold's new return type. Now, the bits that are grayed out are things that we've already considered and don't need to consider again. The problem is that the algorithm that we just saw doesn't meet our requirements anymore. Notably, the bottom 2 requirements are out of date with what we have on screen here. And so we start off by introducing a second detail concept to improve readability of our detail indirectly left foldable, because it will really become unwieldy in a few moments if we don't have a second detail concept. And the way in which we are going to read this detail concept is essentially that the first 3 parameters are exactly the same as the indirectly left foldable, where we have the operation, the T, and the iterator. But then we also have this thing called raw result, which is the invocation's actual result type. And then we have decayed result, which is the invocation's result type, but where the result type has been decayed. And we'll get to why that's important in a few slides' time. But what's important here is that decayed result and the R that you see on screen on line 4 are describing the same thing. So let's press on to the new expressions. We have 3 new expressions that we want to be considering. Let's start off with the simplest one, which is this thing that we're going to be returning in the base case where the range is empty. We're just simply going to convert the initial value into R. And what we're doing here is we are converting our T into R. And that means that T needs to be convertible to the decayed result. And so that's the first requirement. The second one is that we have a new invocation and we need to consider this new invocation. What we're saying is that when we invoke op, the first parameter will have the type R because that's our new accumulator object. And the second parameter will still have the iterator's reference type. So this means that the operation needs to be invocable with respect to the decayed result and the iterator's reference type. Now, if we come back here, we see that that the expression is the same as the initial one where we had init instead of accum. And that means that the decayed result also needs to be movable just like init. And then similarly, the result of invoking op with respect to the new accumulator and the value at the first element. So the value at whatever the iterator is pointing to may be a different type to the accumulator. So we need to ensure that the result of the invocation is assignable to accum. And so we get this nice mouthful down the bottom, which is describing exactly that. And then finally, we get to the reason that the decay is important. The operation could return something like a reference, but per the rules of auto, the type will decay at the declaration. And so what we want to say here is that the raw result is convertible to the decayed result. And here I've thrown a bunch of different requirements at you. So I'm just going to bundle them all together and put them into this indirectly left foldable implementation. And so we have 2 detail concepts. Again, these are not the user-facing concepts that we're interested in. And this will bring us to the end of Act 2. I'm going to posit 2 questions for you. Both of them are essentially, can we compute these operations faster? We'll cover this in Act 3. But now that we've reached the end of Act 2, I'm going to field a bunch of questions for the next minute or so. So the question on screen is, the left foldable concept looks like a concept designed for a single algorithm. And that is correct. You've anticipated one of the questions in my epilogue where I anticipate this question. So that's great. Essentially, yes, that's why it's a detailed concept. It is a detailed concept because it's only being addressed it's only addressing one very specific algorithm. We're about to cover something that is much more general, much more applicable to a broad range of things, and that will not be in the detail namespace. Does that answer the question? Is there an invocable concept that has a return type? Unfortunately, no. That is something that we will, I think, be looking at how to model that. But no, invocable does not address that requirement. We would need to then talk about that as a separate requirement. Okay, I'm gonna push all questions to the end of the talk now. We are doing good for time, so I think we'll get to the epilogue. So Act 3 is reducing to a user-facing concept. Now, at the very end of Act 2, I asked, can we compute these operations faster? And the answer is maybe. We might be able to do it. Now, there's this thing called loop unrolling where where either we or the compiler will analyze a loop and then see what can be done to do more things and take advantage of instruction level parallelism. I'm not going to go into instruction level parallelism, but I do have some resources at the very end of the talk that, if you're interested in this topic, then you can go and look more into it. Now, if we unroll the loop by hand for the max element case, which is the second one, we can see that on GCC for the fold left is considerably slower than the benchmark that I wrote for the loop unrolled fold left, which we are going to be calling reduce. I'll get into that in just a moment. Now, the reason for this is because what fold left does is he considers every element in sequence, and it just kind of combines them all together and goes from left to right in order. But with loop unrolling, what we can do is we can consider multiple elements in parallel, and then once we've executed those operations at the same time or near the same time, we can then combine them into a new result, and then combine that into the accumulation, and then loop back and continue doing this until we run out of elements. So this is what loop unrolling can achieve. But what I need to stress here before we press on is that you always need to benchmark this stuff before you try to optimize your code by hand. The product computation, which is the one at the top, produces a very different result. The product operation for the left fold, where it hasn't been unrolled, is slower than the unrolled one for GCC. But when I switched to Clang, I found that the product operation for the flat for loop is much faster than its reduce counterpart. And that was surprising to me. So I chatted with a friend who is an expert in compiler optimizations, and they said that optimizers pretty much take a back seat whenever a programmer tries to outsmart the optimizer. I had expected that in the worst case, they would be in parity, but it turns out that is not necessarily the case. So before you try and do loop unrolling in your own algorithms, please do benchmark both the naive case and the programmer smart case. We're still going to go ahead and take a look at an unrolled version of this fold left, because it does introduce some interesting ideas. And the unrolled version of fold left in C++ is called reduce, because std reduce has a few extra requirements on it that allow us to take advantage of things like parallelism in both at the instruction level and, if possible, at the data level. We are only going to be looking at something that could ever take advantage of instruction level parallelism, but these requirements will transcend onto the data level one if you do more analysis onto that. So that's why we're going to call this new algorithm reduce, which means that we're essentially breaking away from the left fold and saying, hey, I understand that left fold is going to produce a very distinct thing, but we want to do a bit more and take advantage of that. So let's take a range as reduce. The shape of this algorithm should feel at least a little bit the same as the left fold. I've grayed out everything that is very common between the two operations. Essentially, what we're doing here by unrolling this is we're doing the left fold, and then also, but we're unrolling some of the loop for the situation where we have at least 4 elements. And sorry, this is actually something that libstd C++'s std reduce takes advantage of. And then when we have fewer than 4 elements, we're going to default back to the fold left algorithm. And what this means is that all of the requirements that we had for our left fold are now inherently requirements for reduce, because we are using fold left. And this means that the requirements of fold left are the basis for reduce. So that's the first requirement here. Now let's take a look, like we did with the second iteration of fold left, at what reduce's new expressions are. So we have 6 of them, and what we'll do is we'll bat 3 of them out immediately by looking at the new iterator requirements. So the first requirement is that we want to be able to say last minus first. That's a syntax requirement. We also want to compute the distance. We also want this expression last minus first to compute the distance between the elements from first through to the last iterator, or sentinel if it's a sentinel. That's a semantic requirement. How many elements are there in this range? And then finally, we want this operation to happen in constant time, because otherwise we may as well just walk through and count them, but that's not going to give us an optimization opportunity. So those are the 3 requirements for this first expression, last minus first. Then we have first plus equals 4, where we are saying we want to, instead of just going through every element sequentially, we want to be able to skip an arbitrary number of elements, and we want to do that in constant time. And then finally, we want to be able to index arbitrary elements in constant time as well. Again, this is so we don't have to skip over them and then dereference them. We can just do this all in a nice package syntax. Now, there's only one concept in that describes these requirements, and is also the base concept, and that's random access iterator. So what we're saying is that for this particular implementation that we had on screen a few moments ago, we want to have a random access iterator. And once we know that, we can move on to the more interesting concepts. So the first one is that our operation is now required to be invocable when the iterator's reference type is both the first parameter and the second parameter. This is an important thing, that because we actually do this twice. But it would be very frustrating if the first parameter and the third parameter were equal, and then the second parameter and the fourth parameter were equal. But when we passed them in as elements to our operation, we got back different answers. This is okay for left fold, because left fold is super general and you can get away with it there. But for something such as reduce, which is often used for numerical things, or simply because we are doing things now in parallel, we want these results to be the same. It would be extremely frustrating if first of 0 and first of 2 were the number 100, and then first of 1 and first of 3 were the number 50, and our operation was addition, but we got back 150 for the first one and 300 for the second one. That's just not cool for our for our requirements. So what we say is that we are going to strengthen or refine our invocable requirement to be regular invocable. Now, regular invocable, what that means is that not only can we invoke with respect to our parameters, but also we're not allowed to modify the parameters, and we're not allowed to modify whatever it is that we're calling, and that if we're given equal inputs, we always need to give back equal outputs. That's what regular invocable means. Equal inputs yield equal outputs for some function. And so this is the new requirement on op. Just for all of our, wherever we set invoke, it will now need to be a regular invocable. And then because we are doing a bunch of conversions from the operation to R, we need to say that the invocation's result is convertible to R, which is our return type. And so this brings us to the end of the really trivial sort of, I say trivial in air quotes here, requirements. That is that we've stayed within, when I say trivial, what I mean is we've stayed within the realm of C++. We haven't had to stray into abstract algebra. And so now we're going to walk into the area of mathematics, take a look at a few definitions and bring those definitions into the world of C++ based on what our requirements are for this algorithm. So the first thing is that we need to think about the term operation. We've been using that very loosely as some sort of thing that we call. In mathematics, according to Wikipedia, an operation is a function that takes some number of values as inputs as parameters or operands and returns a well-defined output value. It has what's known as a domain and a codomain. The domain is the sets of values for its inputs, and the codomain is what it gives the set of values that could be its output. Now, what's really interesting to us is not necessarily the domain, but the domain of definition. Essentially, the domain of definition is the subset of the domain that the operation is defined for. Now, if we take the square root operation in the space of real numbers, we can see that the domain is going to be the set of real numbers, but the domain of definition is going to be the set of non-negative real numbers. And that means that the square root of -1 in the real number space is invalid. With the domain of definition, if we don't pass in something to our operation that's inside the domain of definition in programming, then we're not necessarily going to get back something that's sensical. We could get back a meaningful result. We could get back something that's completely nonsense. In C++, this is really divided into three different contexts. Three different categories depending on the context. There's undefined behavior, which has a lot of coverage on. There's ill-formed no diagnostic required, which is that really weird one that Titus and Chandler talk about in their What is C++ video from CppCon 2019. And then finally, there's unspecified behavior. And depending on the situation, if you're outside the domain of definition, you could fall into any of those three categories. Or you could have some sort of well-defined behavior, such as throwing an exception. But this is essentially why floats are totally ordered, despite being unable to compare NaN values. Because NaNs are not in the space of the real numbers, and they're also not in the space of comparable things for floating point arithmetic. And so the fact that they are not, those specific values are not comparable is okay, because they're outside the domain of definition. We don't care about that in generic programming. And now that we've covered the definition of what an operation is and the definition of the domain of definition, we can start thinking about a binary operation concept. Now, there are three constraints for a binary operation in this context. It needs to be regular invocable because it's related to the reduction algorithm. It needs to, the result type needs to be constructible as a parameter that we can pass to R. And it also needs to be assignable to an object of type R. Now, these two latter requirements are precisely to prevent us from returning something that is extremely arbitrary and also prevents us from having a void returning operation. Now, this binary operation has some axioms that are associated with it. The first of which is that the types T and U represent the operation's domain. When one of the mathematicians who reviewed my deck of slides weighed in, they were concerned that T and U were going to restrict everything down to a particular set, and there wasn't going to be allowed to be any cross set or cross type operations. That's not the case here. We can not only have different types as our input parameters, we can also have different sets. So this binary operation should work, for example, for scalar vector multiplication. The second requirement is that the type R represents the operation's codomain. Again, it's allowed to be a different set and a different type to T and U. And then finally, the value returned by the invocation needs to be an element of the operation's codomain. So it can't, for example, if we had something such as addition on floats, on real numbers, we can't return back a NaN value that's outside the operation's codomain of definition, which is like the domain of definition, but for the codomain. You may also know that as the range. That's kind of confusing when we think about C++ ranges. Okay, so we now have the definition of a binary operation concept. We're going to use this to build up what's called a magma. Now, Steve talked about magmas in his session before this one, but if you don't have a strong understanding of abstract algebra, it'd be good for me to restate it. Essentially, a magma is some binary operation where its domain and codomain are the same. That's basically it. And it's very general. It's in fact too general for most interesting use cases. So we make this another detailed concept, and we say that the inputs need to for some types T and U as inputs, they need to be the parameter types in any permutation of T and U, and essentially that forms what a magma is. So we have 4 different binary operations with the parameters, with the different orderings of T and U as parameters, and the return type is constant. And then we have some axioms. It's a bit wordy, but hopefully shouldn't be too difficult to understand. Essentially, given some instance of the operation and a T and a U, sorry, a T1 and a T2 of type T and a U1 and a U2 of type U, the domain and codomain of the operation need to be the same. That meets the definition of a magma. And then because we have a cross type operation here, what we need to say is that the types are both representing the same domain. That's inherited from the binary operation concept. But what we also need to say is that if T1 equals U1 and T2 equals U2, provided that the one concept is on the left and the one variable is on the left and the two variable is on the right, the operation is always going to return the same result. That means that when we apply the operation with T1 and T2, it's going to equal the same as the invocation of the operation when we apply it with T1 and U2, and similarly for the other permutations. So this is the definition of a magma in concept form. Then we move on to an axiom that you might overlook. And so we have 3 of the expressions that are in our reduction algorithm on screen here. And so we have, let's consider a range of 1, 2, 3, and 4. If we do addition, we have x equals 1 plus 2, that's 3, and y equals 3 plus 4, that's 7. So z, which is x plus y, should be 10. And if we shift the way in which we do our addition, so we have x equals 2 plus 3, that's 5. We have y equals x plus 4, that's 9. And z equals 1 plus y is 10. So these two results are the same, all we've really done is rotated the way in which we do our addition. And let's change up the operation from addition to subtraction. So we have 1 minus 2 is -1. We'll make that x. We'll say that y equals 3 minus 4. That's -1, and z equals x minus y. That's 0. So our results are going to be different because we're doing a different operation. That's only natural. And the order in which we're doing the operations should match. It matches the left-hand side of the addition case. Now let's consider the right-hand side of the addition case with the subtraction operation. So we're shifting again 1 to the left. 1 to the right. We have x equals 2 minus 3. That's -1. So far, so good. It matches the initial x for subtraction. Then we have y equals x minus 4. That's -5, which is not the same as our left-hand side. And then when we compute z as 1 minus y, which is 1 minus -5, we end up with 6, +6. And those results are not the same. So that means that we have a different situation here. And this is true for multiplication as well as this is true when we replace addition with multiplication and subtraction with division. So this transcends just addition and subtraction. So this is what we call associativity. Now, informally, associativity basically means that we can rearrange the parentheses on a sequence of operations that are the same, and it will yield the same result. So if we look at how I've reordered the parentheses on the left-hand side with addition, we're always ending up with 10. But when we do that for subtraction, we end up with a different answer every time. That means that addition is associative and subtraction is not associative. This is important for what we're going to be talking about. So I'm going to define it a bit more formally. The formal mathematical definition is on screen. This translates roughly to this C++ code. We're not going to consider requirements here because it's really just an analogy of what the two should look like. And once we understand what associativity is and recognize that this is important for our reduction algorithm, we can start thinking about the algebraic structure called semigroup. Now, semigroup is some magma whose operation obeys the associative property. That's it. And here we come to the constraints. And we say that a semigroup is a magma when we can pass in a t and a u as our two parameters, and then when we can pass in a t and the invocations result of that t and u as our second parameter, and then we flip it so that way the invocations result is the first parameter and u is the second parameter. And the reason we have these three things is because instead of just sticking on a requirement where we say the invocation needs to be associative, which is what this axiom is saying very wordly, is because we want to be able to check that. And the only way we can really get to checking that is to say that this result what's returned needs to also be something that we can pass into the operation. And I want to pause here for a second. There's something different about this particular concept than everything else that we've talked about up until this point. All the other concepts have been inside the detail namespace. This one isn't. It's user-facing, and that's important because this is the concept that we've been walking towards. The reason that it is a public concept and is user-facing as opposed to everything else that we've considered is because it covers a broad range of situations, and even though we haven't talked about them formally, I can reason about some of them as well. So, for example, stuff like addition and subtraction are both semigroups. In the context of this talk, where we haven't talked about some of the stronger requirements, this would be something that's applicable to those particular things. And So because it applies to a much broader range of things, we can say that semigroup is a user-facing concept. Now let's go and put on our requirements. We say that our iterator is now has a random access requirement. We are going to require that our operation models a semigroup with respect to the reference of I as both its first and second parameters, and the result type is as what we're getting back from it. Those correspond to the highlighted lines 13 and 14. And then we're also going to say that the result type of the operation is going to be its two parameters as well. And that needs to form a semigroup, and that corresponds to lines 16 and 17. It was previously 13 and 14, but because we've added a new requirement, it's bumped the lines by one. Those highlighted lines are corresponding. And that brings us to the end of Act 3. We have finally found a user-facing concept that still describes the requirements of our algorithm. Now, we do have time for the epilogue, so I'm going to defer all questions to the very end. We've already addressed why some concepts are public and others are private. We covered that both in at the end of Act 2 and in Act 3 as well. So let's move on back to the question of, can we write a container or a number concept? And the answer is still no. Concepts are not the same as interfaces. What you need to do with concepts is outline the minimum necessary set of things for your algorithm to work. You can do a lot of things with number, but most of those aren't really necessary all the time. And so we don't want to have a number concept because it's not really a useful thing for our algorithms. Semigroup, monoid group, those sorts of things are useful for concepts because they describe operations and the relationships between what we are passing in and what we may get out. But they're describing the operations of our algorithm. They're not classifying some family of types. On that, about containers, a concept that concerns itself with inserting elements into a range, I find that to be far more useful than some sort of vague container concept that just goes, a bunch of things that satisfy this are a container. This area hasn't been explored very well yet. So there's a lot of open research as to what could actually be, what could actually fit into this space. If you were interested in exploring that, I'd be very happy to talk about that with you, but you'd need to be the one that's driving that. And finally, this really comes back to now, well, what we've talked a lot about algorithms, what requirements can I put on my types? It's really the same as the functions, the algorithms we've been talking about. Think about what's critical for your type to simply exist and to participate in its critical algorithms. You may think that this could be clear on inspection, but that's not always the case. Sometimes you do need to derive it from first principles. And as an exercise, I'd like to posit, why do all range adapters in C++20 require that the types that they are adapting model the input range concept? At least to me, that is not something that is visible by inspection. It's something that you need to derive from first principles and really break down what's going on under the hood. So this answers all the initial questions. If you want to learn more about generic programming, from mathematics to generic programming and elements of programming, two really good books. They are really the staples for which I based this talk on, alongside the two talks that I had initially mentioned. If you haven't seen either of those, please do go back and watch them. They'll fill in a few gaps. The site stepanotpapers.com is also really good for finding out more about generic programming. And finally, I did promise some resources on instruction level parallelism. These are the three books that I consulted about this stuff. So in summary, essentially what we've been trying to communicate here is that concepts describe an algorithm's requirements, not the properties of some category of types. That concepts that have broad usage are user-facing, but otherwise they should be implementation details. We need to benchmark our optimizations against the naive implementations. We find requirements by studying our algorithms, and the generic programming starts with concrete use cases. That's how you discover a user-facing concept. Thank you so much for watching. I will be hanging out in GatherTown, and if you're not at the conference, then you can find me on Twitter or on the #include Discord. Thank you. So I see a question or maybe a comment, I'm not sure. The other concepts will be exposed to the users as failing to model the requirements will lead to misbehavior of the algorithm. So the user needs to be aware and satisfy them to use, for example, fold correctly. I assume that by saying that they are not user-facing, they do not have a user-facing name, but is that really helping users? By not exposing the name, we are making it harder to find requirements as they will not be a widely portable name. That's an excellent question. So the requirements still need to be public and they still need to be documented. What I'm more saying here is that they shouldn't be available for a user-facing concept is something that should be available for general consumption, such as std invocable or std regular invocable. Something such as indirectly left foldable. Yes, we need to document it and have it document the requirements for fold, but it really should only be concerning itself with fold as opposed to something that's much more, that's going to cover a lot more cases. That way people don't accidentally start thinking that it's useful for their case when in fact it isn't. Does that answer the question? Okay, I'm going to end the session here, and I'll address further questions in GatherTown. Thank you.